Hello everyone, my name is Francesca Palermo and I am a PhD student at Queen Mary University of London. I'll present today my work on multimodal robotic visual-tactile localization and detection of surface crack. This work has been developed in collaboration with the National Center for Nuclear Robotics and the Tokyo University of Agriculture and Technology. One of the most important tasks for nuclear environment is the detection of fracture on containers of chemical and radioactive waste. These cracks may be caused, for example, by material degradation over time or by environmental changes. The problem is that when they are not detected in time, the fracture may lead to larger catastrophic failures. In the state of the art, there are multiple techniques for detecting fractures. The majority of these techniques rely on acoustic or electric eddy current, which requires sensor installation. Another set of techniques rely on computer vision. The problem with computer vision is that it is not robust when considering low lights or other external factors. In addition, electronics components are heavily affected by nuclear radiation and they cannot accurately perform in nuclear environments. On the other hand, we have tactile and proximity sensing, which can provide useful information on materials, such as, for example, the shape, the texture, and the hardness. For my research, I'm using a finger-shaped tactile and proximity sensor based on fiber optic. This sensor was developed at Queen Mary University of London in the Advanced Robotics Lab by Elisaveta Konstantinova. The sensor is made up of 4 pairs of fiber optics. 3 are used to calculate the deformation of the middle soft part of the sensor, and a couple is positioned to the tip of the finger to calculate the proximity to the surface of the explored surface. Being based on fiber optic, the sensor is robust to gamma radiation. In my previous work, I firstly used tactile data to detect fracture on surfaces. The sensor previously described was attached as end effector to a robot, and the robot was sliding on top of a surface and acquiring the data during the movement. The raw data was then processed, and time domain features such as mean absolute value and root mean square were extracted. And then a random forest classifier was applied to detect the presence of a crack or a flat surface. The problem with this approach is that it needs to explore the whole surface before recognizing a possible fracture, so it requires a lot of time when applied to non-constrained environment and may produce many errors. So imagine, for example, that for exploring a 100 times 200 millimeter surface, it was requiring around 10 minutes. So for this reason, we introduce a multimodal approach of using both vision and force proximity data. So a camera is used to scan the environment and using faster RCNN object detection, it detects the possible area of interest where a crack may be located. These coordinates are then sent to a manipulator, a geomagic in this case, with a previously described sensor attached as end effector, which repositions itself to the sent coordinates and starts the exploration of the area. It then confirms if there is indeed a crack in that location or if it is just a false positive from vision. The setup used in these research and experiments consists of a camera used for object detection fixed on top of the surface. The tactile sensor is attached as an effector of a geomagic optic robot, and there is in addition a laser cut crack table used for the exploration. For the object detection analysis, a faster RCNN with Inception V2 architecture, pre-trained on the COCO dataset, is implemented, which is then fine-tuned on a total of 3000 manually labeled images, showing fractures on various surfaces. The dataset is then split 70% for training and 30% for testing and validation. Since the dataset consists of images of just cracks with no occlusion or other objects in the images, augmentation of the dataset was required. To make the neural network see and recognize other objects, each of the original image is randomly pasted on bigger background images of nuclear power plants. In addition, to avoid the model to rely on just the gray color of the patches, also gray patches with no cracks are randomly pasted in the bigger images. To create a sort of occlusion to the images, a set of screws are also randomly added. Finally, a set of augmentation techniques consisting in horizontal flip, scale, translate, and other techniques is applied to each of the resulting image. To test the algorithm, a series of experiments are performed. So first, two offline experiments are implemented to detect cracks using only visual inspection on the image dataset or using only tactile data on the 3D printed samples. In addition, also two experiments are performed to test the improvement of using the two modalities, so vision and tactile, together. The object detection model is tested using the original image dataset and the dataset obtained with the augmentation steps previously described. It is shown that the model trained with the augmented images outperforms the baseline model by achieving 65% of mean average precision. Regarding the tactile data, the model achieves the best results when trained with the deformation data, D1, D2, and D3, and the proximity data using the engineered extracted features, achieving an average of 90% of classification accuracy. For the online experiments, two experiments are performed to test the efficiency of the multimodal approach. So first, a test to check the online accuracy performance of the model is done, and then experiments to analyze the time required to explore a surface when using only vision or vision plus tactile. For the first experiment, the camera identified the possible location of fractures in the environment and then sends the location to the robot, a geomagic in this case. The robot repositions itself to the correct location and starts the exploration, while the sensor sends data in real time to the random forest classifier via UDP. After one location is explored and the crack is confirmed or rejected, the cycle repeats itself for the rest of the possible identified cracks. To check the algorithm, laser cut cracks are used. Photos of the cracks are also included as false positive from vision. In total, 10 trials are performed, and when using the two modalities together, the accuracy for detecting the cracks reaches a total of 92% of accuracy. Vision alone detected 7 false positive, 1 false negative which is never detected, and 7 cracks. The tactile data failed only one case when considering a crack of 0.5 mm. Detecting a fracture using only tactile data would be really time consuming since the robot will require to perform several surface scanning to find the crack. Because of this, using a combination of tactile and vision would help in reducing this time. For tactile exploration, several scanning movements on the surface are required to localize and detect a crack. And the number of scanning movements in this case was estimated based on the crack geometry, so the length, the shape of the images of the crack, and their spatial frequency. We quantify these assumptions based on the dataset of the crack implemented for object detection. It is found that in the best case scenario for the tactile only exploration, it required around 200 seconds, which is around 3 minutes and a half, to perform the whole experiment. When using both vision and tactile together, the time was reduced to 32 seconds, so half a minute. So, in conclusion, I presented a multimodal fusion model using both visual and tactile to detect cracks in the environment. For future research, edge detection and graph theory will be implemented for motion planning trajectory for a Franka Panda manipulator. In addition, also a reconstruction of the explored surface will be provided to a possible operator for remote inspection. If you have additional questions, please feel free to contact me to the provided email, and thank you so much for your attention.